Welcome back to Chapter 8. In this section, Section 2, we're going to continue looking at quadratic functions. We're going to specifically look at the equations in vertex form. We have a few different forms, way the equations can look. Kind of like with lines, we had slope-intercept, we had point-slope, we had standard form. Same idea. We have a few different forms for quadratics that each have their own benefits. Vertex form is really good when we're using graphs, going back and forth with graphs. So our learning targets, I can graph quadratic functions using the vertex form. So before we get into it, let's see what is the vertex form of a quadratic function. The vertex form of a quadratic function looks like y equals, or f of x equals, a times x minus h squared plus k. We're going to look at what each of these a, h, and k do here in the next few minutes. One thing to notice, however, is that this right here is a minus sign. That means whatever number is in there with x, we have to take h as the opposite of it. So if we had like x plus 2, if this looked like x plus 2 squared, that could be rewritten as x minus negative 2 squared. So h would be negative 2. So it's just backwards of what we think it is. If it was like x minus 1, h is just 1. So I want to give all these things away, but I won't. I will let us look at them as they come. I just wanted to see this equation. This is what we're looking at. So first, let's look at that plus k at the end. So we have the parent function of a quadratic, just y equals x squared. Let's see what happens when we go y equals x squared minus 4. So we have that k. We're going to make that k a negative 4. So if we graph this, this is a graph of y equals x squared. Notice we have our points. We have 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. We could go up to 3, 9, and negative 3, 9. Notice the symmetry there. The y values are the same. When we go 1 away from the vertex, we're at 1. When we go 2 away from the vertex, we're at 4. When we go 3 away from the vertex, we're at 9. It doesn't matter if we go left or right. All right, what would happen if we graph x squared minus 4? We get that, which our vertex is now at 0, negative 4, because we just took this point and we went 4 down. Then we have this one, which is just this point minus 4. We have here, which is this point minus 4. And it goes the same the other direction. So we just took each of those values and we subtracted 4. That shifted the parabola down 4. So what this number does at the end, this plus k, is that's going to be a vertical translation or a vertical shift. It's just going to go up or down by that many. So what about if we had x squared plus 3? If we had g of x equals x squared plus 3, what would we do? We're going to take each of the x squared values and add 3. So instead of being at 0, we're going to be here. Instead of being at 1, we're going to be at 4. Instead of being at 4, we'll be at 7. So we just took everything, we took the x squared and we shifted or translated up 3. It's the exact same shape. Well, it would be if I could draw, but it should be the exact same shape. It's just 3 higher. So the K, again, is that vertical shift or that vertical translation. The vertex on this new one, instead of being at 0, 0, this vertex would be at 0, comma 3, because we went up 3. All right, how about if we have, let's look at that minus h in the middle. So we're going to compare y equals x squared, which is that one, to f of x equals x minus 3 squared. What's this going to do? Well, that k moved it up or down. This one, where we're doing it to the x value, is going to move it over. Did that go the way you thought it was going to go? Remember, it's x minus h. So in this case, h equals 3, not negative 3. Notice here we just took this and we went over 3. It's just backwards looking because of that negative in the equation. Why would that be a negative there? If we plugged in 3, 3 minus 3 equals 0, and we're back to that point. So that's why it's negative. That's how that shift works. But what we did here, so we took all these same points and we just shifted them over 3. It'll be tough to draw these because, so this one goes over to here, this one goes to here, this one goes all the way over to there, and this one goes over to there. They all just get shifted over 3. Notice we have the same shape. The vertex now, instead of 0, 0, is at 3, 0. What if we went x plus 1 squared? Well, remember, this could be rewritten as g of x equals x minus negative 1 squared. So h in this case is negative 1. So we're going to take each of those points and we're going to move it negative 1. So we're going to go to the left 1. Then sketch it. Hey, my sketch was a little bit better that time. So everything just went to the left 1 from that red y equals x squared. The vertex now, instead of at 0, 0, the vertex would be at negative 1, 0. So things to notice here. We had 3, 0, negative 1, 0. When we moved it up and down, instead of 0, 0, we had 0, negative 4, 0, 3. We're using those h values and those k values. So what do these graphs look like? If we have, so just understanding this graph. So if I graph y equals, or f of x equals x minus 1 squared minus 3, notice in this case, h equals 1, k equals negative 3. Where's the vertex? Right here, at the point 1, negative 3. How about if we have this one? X minus 1 squared plus 2. So h again equals 1, k equals 2, the vertex, that point, is 1, comma 2. Here we have x plus 2 minus 1, so h would equal negative 2, k equals negative 1. Look at where that vertex is, negative 2, comma negative 1. So, and these all have just 1, a is 1. We haven't started looking at a yet. We will in a second, but that's not going to change what we're noticing here. Hopefully what you're noticing here. When we have y equals a times x minus h squared plus k, the vertex is at the point h comma k. That's why it's called the vertex form. We can see the vertex right in the equation. You don't even need to graph it. Or, more importantly, that's going to help us graph these things. So, how about that a value? Let's do some changes with a. So we have the red one here is just the x minus 1 squared minus 3. And the blue one is the 2 times x minus 1 squared minus 3. Notice the only thing that's changing is that 2 right in front. What does that do to the parabola? It stretches it vertically, which more noticeably, it pinches it. Notice the parabola is tighter. The blue one is tighter than the red one. The red one's just a little bit wider than that. What if we went the other way? So instead of multiplying by 2, let's multiply by something less than 1. So 0.25 or 1/4. Notice now, instead of the blue one being tighter and inside the red one, it's pulled out, it's fatter, and it's outside the red one. Notice the vertex is the same on both of those. As I mentioned, that a value is not going to change the vertex. All right, well, so we had something bigger than 1. A is bigger than 1. It makes it skinnier. When a is less than 1, that makes it fatter. I'll go wider. All right, but there's a lot of things less than 1. Notice if a equals 1, neither of those is the less than or equal to. If it equals 1, it's the same because it was 1. The red one, a is 1. Well, what if it got smaller and smaller? So it's going to get wider and wider, and then it's going to end up being flat. If a equaled 0, it would be flat. It's not a quadratic. What if we went smaller still and we got negative? It's going to go down. When a is negative, when a is less than 0, it opens down. Notice this one is wider than the other one. That's because the point 1 is less than 1. So we could add absolute values to these. We don't need to worry about the positive or negative sign when we're thinking about whether it's skinnier or wider. It's just either less than 1 or greater than 1, the absolute value of it. The sign, the positive or negative, when it's less than 0, it opens down. When a is greater than 0, it opens up. So that's what the a value does. It changes the actual shape. How wide is it? The h and the k tell us where is the vertex. Where does this parabola start? The vertex is a good starting point. It's a center. A line doesn't really have a center. but a parabola does. So how could we graph it using the vertex form? Well, we're going to start by graphing the vertex. So the vertex here, remember this is x minus -1, so we have the point -1, 5. So we're going to start with the vertex. Then we're going to go, we need a couple extra points. We really need 4 extra points, but we only have to find 2 because of the symmetry. So we're going to go 1 to the right. We could go 1 to the left if we wanted to, but honestly 1 to the right is 0, so that's a good number to plug in. So let's plug in 0. We'll have -2, and then 0 plus 1 squared plus 5. 0 plus 1 is 1. Squared is 1 times -2 is -2 plus 5, which is 3. So f of 0 equals 3. We can plot that point, which means if we went 1 the other direction to -2, that would also equal 3. How does that work? Really, all that is in this step right here, we're either going to have a 1 or a -1. When we square it, that negative doesn't matter. It's going to be a positive number. That's where that symmetry comes from. When we square it, either way we go, it's going to be positive. All right, now let's go another 1 over. So let's plug in 1, because that'll be the next one over. So we'll have -2, 1 plus 1 squared, plus 5. 1 plus 1 is 2. Squared is going to be 4. -2 times 4 is -8. Plus 5 is -3. So at x equals 1, we're going to get -3, which means also so we went to -2. If we go over another one to -3, we'll also get -3, because -3 plus 1 is -2, squared is still 4. So we had to find the vertex and 4 more points, but really we only needed to find 2 more points and then use that symmetry. And now we're going to sketch the parabola. We're going to connect the dots in a parabolic fashion. Don't make straight little line segments. It should not be pointed at the vertex. It should be curved. I do understand there's a bit of an art to it. There's a bit of skill. It's probably not going to happen right away. In fact, it might not happen when I draw it now, but do your best to make it not pointed and make it kind of a smooth curve. So we started with the vertex, then we found 2 points on either side. There are other ways of finding those points, which we might get to. Usually those ways tend to come with practice more than like, hey, this is just a way of doing it. Let's look at another one. So here, I'm going to change my color so we can see the work being different. Our vertex here, we're at 2, 1. So we go over 2, up 1 for the vertex. And then we need to plug in a couple other points. So the last time we went to the right because that was 0 and 1. This time, if we go to the right, we're going to be plugging in 3 and 4. If we go to the left, we'll be plugging in 1 and 0. I like those numbers better. It's going to be the same, but I just like plugging in zeros and ones a lot more. So let's plug in 1. we'll have negative 3 times 1 minus 2 squared plus 1. 1 minus 2 is negative 1. Squared is positive 1. So when we plug in 1, we get negative 3 times 1 plus 1, which will be negative 2. Which means that if we plug in 3, we would also get negative 2. Because when we plug in 3, we have 3 minus 2, which is positive 1 squared, which is still 1. So we get the same exact place. Now, it should make sense that that last one and this one, we can tell they're both opening down. Notice those A values are negative. We had negative 2 and negative 3. They should be opening down. That's a good thing. If they were opening up, we should hopefully check it and see that, oh wait, this isn't good. All right, now let's plug in 0. Negative 3 times 0 minus 2 squared plus 1. So 0 minus 2, that's negative 2 squared is 4. So we have negative 3 times 4 is negative 12 plus 1. F of 0 equals negative 11. Ooh, my graph goes to negative 10, but negative 11 should be right about there. And then same thing over here at 4. Connect the dots. So the bigger that A value gets, the narrower it gets, the harder it is to not make that pointed. When it's a big wide curve, it's a lot easier to keep that as a nice curve. All right, how about this one? Our h value, this is x minus negative 1. So we're at negative 1 and negative 4. So our vertex is negative 1, negative 4. And now we can plug in some values. Let's plug in 0 and 1. F of 0. We'll have 0 plus 1 is 1 squared is 1 minus 4. So f of 0 equals negative 3. Which means that f of negative 2 will also equal negative 3 because of that symmetry. Let's plug in 1. 1 plus 1 squared minus 4. 1 plus 1 is 2. Squared is 4 minus 4. So f of 1 equals 0. Which means that f of negative 3 also equals 0. And notice this one opens up because it's a positive value there. So that's graphing. We start with our vertex and then plug in a couple values on one side, and then you can use symmetry to get to the other side, or you could just plug in a couple values on either side if you really want to. But I would use the symmetry. All right, how about an application problem? What could we do with this? This is a great problem because there's some subtlety in it, and just a lot of things that can happen here. So we have Deshaun and Chris are playing soccer. Chris takes a shot on goal. Deshaun is 3 feet in front of the goal and can reach the top of the 8-foot goal when standing directly beneath it. Can he block the shot from his current position without moving or jumping? All right, so there's a lot going on here. Where do we start? Well, we can start just by kind of simplifying it. So we have Deshaun here, and really, so the goal is at 25. Deshaun is 3 feet in front, so at 22, and can reach 8 feet. So we have the point 22, 8. If the ball, when it goes past 22, if it's bigger than 8, if that y value is bigger than 8, then Deshaun is going to have to jump or move to block it. If it's less than 8, then Deshaun will block it just by standing exactly where he is. So we need to figure out where is the ball going to be at that point. What we have is we have a vertex and we have a point. We can make the equation for the quadratic, for the parabola, from this information. So the vertex being 16, 11, we could plug that in, y equals a times x minus 16 squared plus 11. We can plug it in, right? The h and the k goes right into the form. It's not quite there yet because we still have that a value. That's going to be an actual number. How do we find that? We find that using this other point that we're given, 2, 1.2. Plug those in for x and y. So y is 1.2 equals a times x, which was 2, minus 16 squared plus 11. So we can subtract 11. So 1.2 minus 11 is negative 9.8 equals a times 2 minus 16 squared um, 2 minus 16 is negative 14 squared. We can square that negative 14 to get 196, and we can divide by that 196 to get a equals negative 0.05. So a equals negative 0.05, that's not the answer because we need a point. We're looking for the equation, so we're going to plug that right back in up here to get y equals negative 0.05 times x minus 16 squared plus 11. So that's our equation. It's negative, which should make sense, being that it's opening downward. I mean, this is our parabola right here. It's opening downward. And that a value is less than 1 because it looks kind of wide here. So that's the equation. The equation was not the answer, though. The answer is Deshaun going to hit it? We need to plug in 22 because that's where Deshaun is standing. So we're going to go y equals negative 0.05 times 22 minus 16 squared plus 11. Negative 0.05. 22 minus 16 is 6 squared is 36 plus 11. Negative 0.05 times 36 is going to be negative 1.8 plus 11. When we add those together, we're going to get y equals 9.2. So it's going to be 9.2 feet off the ground when it gets to Deshawn. Deshawn can reach up to 8 feet. Deshawn's going to have to jump or move to get there. Now, is Deshawn going to be able to jump the 1.2 feet? Probably. But the point is, he's going to have to move or jump. Another good question that could come from this is, let's say Deshawn misses it. Is that going to matter? Is it going to make the goal, or is it going to go over top? Well, the goal is 8 feet tall, just like Deshawn, but it's at 25 feet. So let's plug in 25. So here we made x equal 22. Here let's change my color and make x equal 25. So we'll have y equals negative 0.05 times 25 minus 16 squared plus 11. So 25 minus 16 is going to be 9 squared is 81 plus 11. Negative 0.05 times 81 is 4.05, negative 4.05. Add it to 11 is going to get us 6.95 feet off the ground. So if Deshawn doesn't do anything, Chris made a great kick. It's going to go right over Deshawn, right into the goal. So it will go in the goal if Deshawn misses. And we found that by plugging in the x value at 25 and saw that, hey, it's going to hit right about there. Whereas Deshawn, it's going to hit here. So if we followed that arc, it would go kind of like that. So that's an application for these quadratic functions. In vertex form specifically, we saw how we can write it in vertex form. We can write the equation from some information in the graph. If we know the vertex and a point, we can write the equation and then use it by plugging in information we know. Sometimes we just need to take away some of the context of the problem so we can focus on these things. For instance, here, we needed this point, 22, 8. Was it going to be higher than 8 or lower than 8 at 22? And then we did the same thing at 25. So this has been the vertex form of a quadratic function. Don't forget to change that sign on the h value. It's x minus h. But I will see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.